We expect over 30 billion devices connected to the internet by 2023. That is 4 times the world population. Many smart systems like cars, buildings, medical devices need computing at the edge of the internet so they don't have to wait for the cloud to send a control signal. For example, for the autonomous car to make a decision on the road. Many future decision support systems would rely on edge devices to actually do a lot of the data processing and analytics tasks. Cloud service providers like Amazon and Google, they provide excellent fault tolerance infrastructure, or they also provide you tools to build fault tolerance tailored for your application. However, when you have an edge device, we still don't have a good fault tolerance solution from the data management perspective. So my project investigates approaches to provide efficient fault tolerant solutions for edge devices. There are many advantages to edge computing. When you have a computer sitting at the edge of the internet, given the proximity to data, your latencies are better. Since the data is local, better privacy, security, and your data transfer is also much more efficient. Coming to costs, a recent study done by Vicky Bond on a real world use case where they were transmitting IoT data from a wind farm to a remote cloud. And over a 3 year period, what they noticed was that the costs compared between having everything on the cloud versus edge plus cloud scenario where your data traffic is reduced by 95%, you actually save 2/3 of your cost with edge plus cloud solution versus putting everything in the cloud. Edge has many challenges. When these edge devices are consuming streams from multiple IoT devices, how do you scale depending on the dynamic workloads? How do you manage these workloads across the edge network? How do you distribute the workload between the edge and the cloud? How do you manage these edge devices to achieve better performance, better throughput? How do you improve security, privacy? How do you maintain consistency with information produced from multiple edge devices? And also how you provide fault tolerance. So these are all important challenges that need to be tackled. Um, Having hardware replication does not necessarily mean fault tolerance. While you can have redundant hardware, network, power supply to manage failures, given that these devices are on a network and the internet, we should expect message delays and part of the data that might be corrupted, inaccessible, and so on. Um, and with edge devices getting more and more complicated with different hardware, firmware, device drivers, file systems, etc., we need an edge stack that looks at fault tolerance as an integrated component in the architecture that is able to both detect the fault and also recover. So fault tolerance as a research area is or subject is not new. The edge devices have been used in many mission critical applications like aircraft, for example, or military, where where you try to isolate the different hardware components so that you have a high available system. But the challenge is that these are very, very expensive and cost thousands of dollars, and these do not necessarily work in a pure distributed context because you're talking about multiple edge devices that need to communicate with each other, that need to synchronize with each other, and so on. So there is a huge body of existing work both in the data stream management system where you have Apache Spark, Millville, Samza, Storm, where they provide a mechanism to either implement fault tolerance or provide some form of fault tolerance. But these are designed for streaming jobs that run on a single cluster. And also the existing body of research that has looked at low-cost strategies for processing high volume, high velocity data streams work on a single cluster, but not in a distributed edge network scenario. So this problem is very important and relevant. So how is this problem relevant to the current CVDI industry? Edge is a new disruption, especially for companies that are dealing with sensors or IoT. And every company in the medical, defense, IT, health, they all deal with edge devices. Uh, and many companies, like for example Dell, 4 months ago announced $1 billion investment into edge computing, and another real estate firm very recently, a couple of months ago, announced $2 billion investment into a startup for creating edge data centers that would be integrated into their buildings. So this is the edge component is important for decision informatics because a significant component of the analytics and data processing will be done at the edge, whether it is cars, buildings, medical devices, and so on. And without a strong management component in the edge device, these devices would be unusable. And fault tolerance, effective fault tolerance methods are critical for the success of edge computing. Also, this project will use real-world test data from a smart building scenario, which Tieto has agreed to provide to successfully carry out this project. So the project has two goals. First, we want to understand how existing state-of-the-art fault tolerance methods that are already available for managing high volume, high velocity streaming data work in the context of an edge network. Okay. So second, we want to investigate partial replication strategies for distributed fault tolerance. Since fault tolerance strategy also depends on the type of application and the type of workload, we will use a real-world smart building data set to investigate this problem. So in order to accomplish goal one, first we'll create a test bed for investigating fault tolerance approaches for edge devices. We already have a test bed that we created as part of another NSF funded effort to handle fault tolerance for video streams. And within this mesh network that has these 4 edge devices, basically you can introduce a failure into any of these devices, and then the other devices take over. The controller, network controller, provide fault tolerance to read out the traffic using other edge devices. So this particular test bed will be used to test various fault tolerance protocols. We will inject different types of faults into the edge network, and we will evaluate how the different fault tolerance strategies would work, and see the impact on latency, throughput, recovery costs, and so on. In order to accomplish goal 2, which is to develop new data replication strategies for providing fault tolerance for edge devices that process data streams. First, we will investigate partial data replication strategies. for distributed stream processing. So there are basically three different types of replication strategies. One is active replication, where you basically send a copy of the stream to two different consumers, and if one fails, you have a backup. Obviously, it's very expensive, but it has some advantages. And then there is a passive replication, which is looking at checkpointing the state of the stream at regular intervals, so that whenever there's a failure, you're able to go back and recover, from where you lost. And then third is called upstream backup. This method works by creating a buffer at the edge node, and if there is a if the and you receive an acknowledgement from the receiver for all the packets that were sent from the edge device. So if the edge device doesn't receive acknowledgement, then it would assume that this packet transmission has failed. So each of these strategies, they have costs associated with them, and they have their own advantages. So we are going to investigate if we can intelligently combine data processing like sampling strategies along with a combination of these strategies to obtain better fault tolerance approaches. So we are going to study the smart building workload. We're going to work with Tieto, one of the companies that has agreed to provide some data so we can better understand the type of data, the type of processing that needs to be done, and so on. And we're going to use this workload as a case study to investigate our replication strategies. We're going to conduct these experiments on our existing edge network, and we will share the proof of concept and results from our experiments. So the following are the deliverables for this project. The project will offer new insights into fault tolerance strategies for edge devices. We will also produce a survey paper on our findings. The new algorithms or tools that we develop are applicable in many applications like smart buildings, public safety, medical fields, and so on. And we will also publish our findings upon approval from our IAB. So that concludes my project. Thank you very much. Impacts. The knowledge from this project will help us understand the strengths and limitations of different fault tolerance approaches. That includes active replication, partial replication, and upstream backup. The new fault tolerance approaches that will be developed as part of this project will contribute to improved management of edge devices, just like the cloud. When the data is in the cloud, you're not worried about the infrastructure component, whereas when you're using an edge device, it is not clear, how the management is done and so on. So I think this knowledge will certainly contribute to advancing research in this space. In terms of broader impacts, again, organizations will be able to save costs, through better fault tolerance approaches, it'll minimize hardware replication and improve efficiency, and save costs in return. Also, most of the work in this project will be carried out by two PhD students, Tarek Idris and Haytham Idris, both of them working in the IoT space. The project duration is 1 year, from July 2018 to June 2019. Most of the budget is going towards supporting the students, and we're asking $84,000 to complete all the deliverables of this project. And these are the references for this project, and I thank you very much for your time. If you have any questions, don't hesitate to contact me at raju, raju at louisiana.edu. Thank you.